Good morning, good evening, everyone. My name is Mansoor Tivana. I am product manager of Ansys Twin Builder, and together with me today is Clement Quick from Modelon. He's expert in modeling and simulation. So today the agenda looks like something like this, that I'm gonna start with the brief introduction of what Ansys Twin Builder is and what its some capabilities are. And then Clement is going to take us through the key benefits of Ansys Twin Builder Power Library, which contains hydraulics and pneumatic libraries. And he's going to take us through what's the key capabilities, their content and key applications are. And finally, he's going to show some of the examples, real-world examples, how the Fluid Power Library in action looks like. So I'm going to start with the key capabilities of Ansys Twin Builder. So we have three key capabilities, what we call build, validate, and deploy. Build allow us to build system simulation that's physics-based, and by using simulation, you can also deploy them in digital as digital twins. Then we have system validation and optimization, which allows you to validate your system models either by bringing in the test data or by combining them with the optimizer and to see how to optimize the behavior of your system model. And finally, of course, you can deploy them on an IoT platform to perform system predictive maintenance. So talking about some key capabilities, getting into a little bit more deeper into the technology side. On the build phase, we allow our customer to build a number of system models by using a number of different domains and languages. Modelica plays a very big role in that, and also the hydraulic and fluid power library that's also is based on the Modelica language. In addition to that, we also have libraries in VHDML, AMS, and CC++ and Spice, and some more. So these libraries are as drag and drop libraries. That means that if you want to model a resistor, you just drag the resistor out of the library and place it on the Twin Builder schematic. If you want to model a cylinder, you just drag the cylinder and drop it, and then you can parameterize it. We also allow to bring in third-party tools or modeling done in third-party tools. So by support of FMI FMU. FMI FMU is a standard that allows the interoperability between different models. So a number of Ansys 3D solver allows this standard, and also we do co-simulation with 3D solvers. Another technique to bring in the 3D model is called reduced order model that allows you to simplify your 3D physics by not compromising on its accuracy. But these reduced order models are very fast and can be used in system simulation. And finally, we also allow to bring in embedded software integration. You can bring in the software from and do complete model in the loop or software in the loop simulations. On the validation, we have a number of post-processing capability. You can plot a number of different regular plots like 2D plots and also 3D plots. And we also allow rapid HMI prototyping. That means you can build these widgets, which allows you to interact uh, with the simulation, these buttons and graphic panels that that facilitate the interaction with the simulation. And finally, we have system validation and optimization that allows parameter sweep, design of experiments, and we also have scripting language support. That means that you can do or automate these optimizations using VBA or Iron Python scripts. As I said before, we allow seal integration. That's means model in the loop and software in the loop validation workflow. In addition to that, we also support external optimizer, for example, Ansys DX and Ansys OptiSlang. Talking about the deployment capabilities, so we have a very close cooperation with a number of IoT platforms, including SAP and PTC, that allows you to export these system models and deploy them into IoT cloud or on the edge device. And we also provide an SDK that allows you to deploy these twin models, or we call them dot twins, to deploy without deploying the whole twin builder. So that means these are very portable models that can be operated using the software development kit. So Twin Builder provides a unique approach to system modeling that includes building of system models using these system libraries. You can bring in these validated 3D physics model through either as a whole or as a reduced order model. That makes more sense for the system simulation to bring them as a compacted model. And then we add solver to that, and you can do system simulation on that. And if you are interested, you can either export that to the cloud, or you can also export them as a co-simulation FMU to be deployed with other tools. So now I'm going to hand over to Clément, who is going to present Twin Builder Fluid Power Libraries.
Clément, we're not hearing you. You might be muted.
Can you hear me?
Yes.
Okay, sorry for that. So if I can get back to the library, just to the previous slide. So the Ansys Twin Builder Fluid Power Library contains both model on hydraulics library and model on pneumatics library. We will first go to the key capabilities of our libraries in general in Modelon, and then we will discuss each hydraulics and pneumatics library separately. So Modelon has several libraries, and all of them are Modelica based, which provide an unrivaled flexibility because our libraries are protected from modifications, which means that end user cannot modify it unintentionally. On the other side, the component, all the codes are visible, and you can duplicate a component and modify it. So the library remains what it is, but you can still take every component and extend it for further use if you want. It is easy to use yet powerful because there are many predefined components. So it's easy for a new user to just drag and drop a component, parameterize it, and simulate. On the other side, if you're an experienced user, then you can actually extend the model for more. If you have some specific correlations that you want to implement, you can implement them in on the base of the model we provide. It's well suited for control design and validation of your control loops, for example. And it's really a true multi-engineering tool because there are every domain which are covered in Modelica code, and you can connect them together and most of the library we provide, they can be interconnected together. So for example, pneumatics and hydraulics are connected together. They are based on the Modelica language, but there are other libraries also that you can connect with this. Let's focus first on hydraulics library. It's a library for hydraulics in the meaning of fluid power. So it covers high pressures. You can have up to several hundred bars. The flow compressibility is modeled. You have the inertia of the flow that is also modeled. All the pressure losses are modeled. And you can switch easily from hydrothermal model to thermohydraulics by one click. So a model that you develop for hydrothermal use is easily providing thermohydraulics results also. There are many components already available in the library. We'll go through it in the next slides for both mobile and stationary applications. And you can do more, as I said before, because of the way we build the library. There are many building blocks, and you can just increase the model with your own correlation if you want. It's well suited for many applications. I listed here a few, and at the end of this slide, we also see other applications. We have a standard package order, which includes information, which is the documentation of the library of the package in which we are, some example interfaces, templates that you can use to build your own model. I don't know if I can have a pointer here. And components by type. So you see here information example, interface templates, and then components, actually accumulator, cylinders, many components. And if you look in one of these, for example, rotary actuator, you will find out the same package order interface. And what you can see then is there is basic here, and there are some components here. So these components here at top level can be directly drag and dropped and are for, let's say, all users. The parameterization is a bit eased, so it's easier to parameterize. Basic package include actually the base component that are used to develop this component here, top level, and they are for more experienced user. You might have more to parameterize on it, but also you can get more, of course, out of it. So let's see some more components. In the cylinder package, you have the actin cylinder, differential plunger cylinder. You have lines, which could be rigid hoses. You can have discretized line to see some, for example, water hammer effects. There are pressure and flow sources. There are rotary actuator, which could be either ideal or with losses, for example, included inside. There are many valves. Let's say the control valve might be of interest. Directional control valve is the main package, but there are also, for example, proportional valves inside this package in BASIC, and they are used to construct the directional control valve. And you have spool dynamics that can be modeled, some hysteresis effect also. There is a package which is called Element here, which is really interesting. You can actually have really detailed physical effects for all the models, and that is used for component design. For example, if you look at this spool here, there is the restriction of the spool based on the position that is modeled, and the flow forces of the fluid when the restriction increase, the flow increase also, and there is a force that actually tends to call back the spool to close. This flow, for example, is modeled. So meaning that if you use this component, you will actually see the force at the flange generated by the hydraulic fluid through the restriction. So this element is really is a package that is really good if you want to make a detailed design of a valve, for example, of a cylinder. And there are other many valves such as check valve, pilotic check valves, pressure limiting, or flow valves. So there are many accumulators, well, spring, gas charge accumulator, sensors for flow pressure, temperature. There are also non-ideal sensors if you want to include faults on your sensor, which could be really interesting when you're doing digital twins. You might want to study the response to fault of your system, of your then model, and actually sensors might be a source of fault. So it's really interesting to have non-ideal sensor here. Many restrictions. We will cover more on the last view, but of this library. But there is laminar, turbulent. You can model cavitational effects in some orifice. The geometry-based fitting, so you can have bended channels. And we have also volumes, closed, open chambers, which are a function of the position they are used, for example, in a piston accumulator or a piston cylinder. And there are also many fluids already defined. Just drag and drop the fluid, and then it's applied to the component you have at this level. There are fluids which are, let's say, faster but less physical with constant properties. But there are also thermohydraulic fluids. There are fluids which are tabular, table-based. If you like to have only the parameters from a standard, which are usually tables, then you can either use the one we have, either build your own. But the view of like more view of the libraries, and for example, what I was talking before, in the restriction we have fittings with many fittings, such as, for example, a thick edge, single edge, straight pipe. The channel could be kind of a pipe which could have the shape you want, not necessarily only circular shape of a pipe, for example. Could be square. You see all the predefined directional control valve, and on the elements, the specific detailed effect, for example, propel lift with a cone shape or with a sharp edge on the sleeve. The key applications, mostly I would say all the industry are covered with this library, and we have customers in all the industries. So mobile, in aerospace for flight controls, typically the braking or power steering of cars and motor trucks. Landing gears also on aircraft, typically. Now we can switch to the pneumatic library. You will see that it is really similar to hydraulics in terms of packaging and in terms of capabilities. So it's based on ideal gas law assumption. The components are also available, most of them for both mobile and stationary equipment, and you can also build your own. So it's really organized in the same way. And the key capabilities are for typically study system dynamic. In pneumatics, it's even less predictable than in hydraulics in some cases. When there are, for example, antagonist load against your cylinder, that's really useful. You can verify your dimensioning, and you can also make some parameter study. The same standard package order applies, so you should not. You would find the same packaging in both libraries, and the same also applies that you have top-level components, and in basics you have maybe more details, building blocks that are used for the top-level components. If we go through the library also a bit, you would see the cylinder here, double effect. They are cushioning. If you want at the end of the cylinder, it's quite typical in pneumatics. There are long line and capillary lines modeled. There are sources, reservoir, and silencers. In terms of gases, there are constant gases and both ideal and real gases models. So constant gases is good at the beginning, but when you try to be more predictive, you will tend to use ideal or real gas. So there are good real gas model in this library that are quite fast when simulating. You will have also directional control valves, same with first order spool dynamics, and you will also find some elements modeled in this library. If you want to have a detailed model, typically I put this example of a pressure relief valve. One of our customer, for example, does not use the valve pressure relief valve. He modeled his own with elements because then he can have more dynamics modeled. So actually we did it for the customer, but it's a typical example that could be of interest. In terms of restrictions, same apply. We have many fittings that are based on the geometry, and we have also nozzles and orifices. There are rotary actuator and in the linear actuator, I didn't say it, but there are also the below which are modeled, and we have pressure and flow sensors and also chambers. Same here, the view of the library. This is pneumatics, so you see you will actually find many of the fittings I said before. So the bends, the channels, which have the shape, for example, rectangular channels, a thick edge. For the restriction, you have some orifices and nozzle here. And on the elements, you see also that there are, for example, puppet lift. The applications, yeah, mostly I would say it applies everywhere where pneumatics is used, but customers typically would be for trains, braking system, suspensions on car, on constructions, driller and hammer, drills and hammer also, they are quite used. I thought I had a slide before, but that's so I will now talk about some examples of libraries. I will first present this example on hydraulics, and then I will show you an example of again hydraulic, but the same also in pneumatics, and I will try to spend a bit more time on pneumatics. So this is a common rail diesel injector. I will try to explain the model now. So we have, of course, the oil component here. The oil, which is drag and drop at top level, applies to all hydraulic components inside. So they just, all the properties in each of these components refer to this oil defined here. So if you want to change oil, you just have either to select a new oil in this component, either to drag and drop another oil. So on this common rail, you have here the pump, which is modeled by a three cylinder here. Then you have the fuel boost pump, which is here to provide a minimum pressure between 3 or 5 bars. Here we model it as an ideal pressure source of 5 bars. And that avoids to have cavitation in this pump, because if you consume too much flow and you have you start from 0 bar, then you might cavitate. You don't want that. Then you have some check valve. I should take. Okay. So that the pump with the 3 pistons, as I said before. Then you have the check valves to avoid backflow to protect the components. Here you have the volume, which represents the volume of the common rail itself, where the oil is stored at pressure, and this below pressure. So there is the consumption of the injectors, how many you have. It's modeled as an ideal source of consumption. And here you have the pressure regulator of the common rail itself, which is here to limitate the pressure provided by the pump when not consumed by the cylinders. If you simulate that in TwinBuilder, actually I should be able to show you the same graph here. In TwinBuilder, you would see actually at the beginning some ramping in pressure because the initial state was at zero at rest. So we start simulating, the pressure gets higher, and then there are these oscillations, which are a combination of actually the dynamic of the flow provided by the pump, which provide you some ripples, and also the flow flowing through the check valve, which is a restriction that is not ideal, then also enables some overpressure. And you see that after some iteration, you actually have a kind of a cyclic behavior. It's interesting to see that the time is in milliseconds, so the dynamic is quite high. I don't know if you can see the time, 40 milliseconds here, 60 milliseconds here. Second example is a typical example in FlintPower when you want actually to move a load with a cylinder. And that's, I would say that's most of the use cases of fluid power when you actually use the power of the fluid to generate a mechanical power. So in this case, the example is quite basic. We don't see well the valve here, but it's a four-port three-position valve. It's a typical servo valve that you could find in the on the shelf. And we have here a constant flow source pressure regulator to avoid that the pressure exceed a given number when the flow is not consumed. It could be also all that substituted by a pressure regulated valve source, a pressure regulated pump. There is a servo valve to control the flow, to meter it into one chamber or the other chamber of the double effect hydraulic cylinder, and there is an external load with the stiffness and damping of the system, also the load, and could be also equivalent stiffness of the rod. And then you have actually interfaces here on the model made on TwinBuilder, and these interfaces, you can see that that's the servo valve input, that's the overall model I've shown just before, and the cylinder position is the output that is provided to a controller, which is in this case external to the Modelica model on purpose. And you can see that based on this inputs of plus minus 0.1 around a position of 2.5, you have actually the given response of the cylinder here, which is not ideal, of course, because many effects are modeled like the delay of the fluid, the pressure losses through the restrictions. If we get back to this image, and here, and the fact that it faces a load to move. And now we can talk about the analogical example in pneumatics. And actually, I would just show the same input outputs. You have the Boolean control here on the valve, and you have the cylinder position as an output. The cylinder is modeled here with some cushioning, modeled with this row here, and you have the valve here, which takes either from a reservoir, which directly take from the environment the air and compress it at the given pressure, typically 7 bars, and give it back through the silencer, which also has a restriction inside because the silencer usually has a restriction to reduce the noise generated at the output of the gas when releasing the air, typically in the environment. Same here. We take in an open loop, in this case, the Boolean control, and we monitor the cylinder position. And you see that for a normalized input of 0 to 1, you see the response here of the pneumatics with more dynamics. And I should be able to show you this here. In Twin Builder, the same image. So you have everything from the slide. I just took them separately, but that's actually the same information you have here. So the Modelica model with the open loop control, or the open loop input, the command normalized, and the answer of the cylinder with the dynamics due to, for example, compressibility of the gas.